Swayam Prabha. Digital India. Educated India.
Hello and welcome to lecture 2 of module 7, where we are discussing ordinary differential equations, the initial value problem. What we did in yesterday's lecture is to go over the geometric motivation behind the numerical methods for solving an initial value problem. So ODE IVP, initial value problem, is what we are trying to consider in this particular module. Okay, so the problem that we are trying to solve is of the form dy by dt equal to some function f of y comma t, and given y at some time t0 is equal to a value y0. Okay, and what we are interested in getting is the curve, how the value y changes with the time t. Okay, so let us say the actual curve looks something like this, and let us say we are going to start with, say, a y0 value, t0 value over here, and the corresponding value is y0. So what we are going to do in the numerical method to solve this ordinary differential equation is to figure out what the next value of y is going to be as we progress forward in t. Okay, so perhaps the way we will progress is we will go from this point to this point. Okay, so as the time t progresses from t0 to t1 to t2, t3 and so on, we are going to get the yellow curve. The yellow curve is the numerical solution, and the white curve over here is the true value. Okay, and as we have been doing throughout this particular set of lectures, the difference between the true value and the numerical solution is the error. And the objective of the ODE solving technique, that the several ODE solving techniques that we are going to consider in the next few lectures, is we want to use a method that is going to minimize this particular error, this particular deviation between the numerical value and the true value of that integral. Okay, so this was the idea behind using this numerical technique. Then we considered a simplest form of numerical solution to ODEs, and that was the Euler's forward difference method. Okay, and in Euler's method, what we the expression for Euler's explicit method was written as y at I plus 1 equal to yi plus delta t multiplied by f of yi comma ti. Okay, so where f is nothing but the slope that is computed at the point yi ti. So if we look at, or if we look at, say, any point yi ti at this particular location, we find out the slope of the curve, that is function f at y3 t3, that is the value of f that we get, that multiplied by the difference delta t will give you essentially the next point where we are going to reach. Okay, so that is what the Euler's method tries to do, is find out the slope to that particular curve and then move along that slope, and that slope is nothing but some function f, the same function f of yi ti. Okay, so that is the Euler's method. What we said next is that instead of the function f computed at yi ti, we can find a better way of getting this value of the slope. Okay, so instead of f of yi ti, we replace that with s of yi comma ti, and then we concluded the previous lecture 1 of module 7, we concluded by saying that there are several methods which incorporate different ways of finding this particular S, and one family of the methods is known as the Runge-Kutta family of methods. Okay. So, in Runge-Kutta family of methods, what we do is we express our S of yi comma ti as some weighted sum or weighted sum of slopes computed at various points in the interval going from ti to ti plus 1. So, we will write that as w1 k1 plus w2 k2 and so on up to wn kn. This is going to be the expression, a general expression for an nth order RK method, which will represent as RKn. Okay. Euler's method, in one way we can call that as the first order Runge-Kutta method, because in Euler's method we didn't have k2, k3 and so on up to kn, we only had w1, k1, and for Euler's method w1 was equal to 1 and k1 was equal to nothing but f of yi comma ti. That was the Euler's method. Okay. So, when we substitute w equal to 1 and k1 equal to f, we will get s as nothing but equal to f at yi ti, and that is really what we see as the Euler's method for solving the ODE, the numerical solution for the ODE. Okay. Next, what I am going to do is I am going to talk about second order RK methods. That means we will talk about RK2 methods. We will look at the geometric interpretation and then we will derive the expression for the RK2 method using the Taylor series expansion. Okay. The reason why I am going to consider RK2 method is that it is going to be relatively easier to explain and to understand. I am not going to consider RK3, RK4 methods and higher order RK methods, but only give you the final results towards the end of this particular lecture. That is how we are going to progress in this lecture. Okay. So, now the idea behind the RK2 method, let us look at the geometric interpretation of what RK2 method is. Okay. Again we will draw the curve, the true curve y against t. Okay. And this time I will just use a purple chalk to draw the true curve y against t. Let us say the curve looks something like this, and let us say the current value of yi is at this particular location. This is ti and the corresponding value of the dependent variable y is yi. Okay. And now we are interested in using a better method in order to find yi plus 1 at another time, say ti plus 1. Okay. I will instead of calling the difference between ti and ti plus 1 as delta t, I will just call this h. H is nothing but the delta t that we have used so far. The reason why I am going to use h over here rather than delta t is simply because writing all the expression in terms of delta t is going to be just a little bit more tiresome job. With h it is actually just going to be a little bit simpler from notational point of view, but for all practical purposes there is absolutely no difference between h and the delta t that we had used in the previous lecture and also in this particular lecture so far. Okay. So, now what we did with respect to the Euler's method was we found the function f at ti comma yi, okay, and that function was nothing but this particular slope. Okay. So, let us just draw this particular line as the slope that has been computed at yi comma ti. Okay. So, what we did in Euler's method was just use that slope projected up to the point at the time ti plus 1, and this particular guy we said was nothing but our yi plus 1, and then we progressed. Okay. what happens is that particular way of solving ODEs is not accurate enough. As we will see later on in this particular lecture, that gives us h to the power 2 accuracy, whereas the Runge-Kutta methods tend to give us a much more accurate way of solving this problem. Okay. So now if we look at the overall geometry, what we will do is we will just complete this particular triangle over here. This distance is nothing but yi plus 1 minus yi, and yi plus 1 minus yi was nothing but f of yi comma ti multiplied by delta t. In this case, instead of delta t, we are using the term h. So this distance is nothing but h multiplied by f yi comma ti. Okay. Now what we do in Runge-Kutta method is that we consider a virtual box over here, okay, where a virtual rectangle over here, where this is the lower edge of the rectangle and this is the right edge of the rectangle, and you can just consider, you know, a rectangle that is formed from right over here, and then we choose a point within that particular rectangle. We are free to choose the point anywhere in that rectangle for now, and then we will try to figure out a numerically better way in order to figure out exactly where we are going to locate that point. So let us say we are going to locate a point somewhere over here. Okay. The t coordinate for this particular point, let us say is going to be p multiplied by h. So we will just drop this particular vertical line over here, and we will call this distance is nothing but p multiplied by h, and this distance is of course going to be 1 minus p multiplied by h. Okay. Likewise, the vertical distances we will call them as q multiplied by h multiplied by f, and 1 minus q multiplied by h multiplied by f. Okay. Okay. So now what we have is we used the function f of yi comma ti in order to find the projection along this particular line. This white line represents the projection on ti plus 1 along the line which has a slope f of yi comma ti. Okay. Then we got this particular virtual rectangle, and in that virtual rectangle we randomly chose a point which is shown by I have just converted into a yellow x over here. Okay. So we randomly chose this particular point. Now this point is at a fractional distance of p from ti and a fractional distance q from yi. Okay. So that is where this point is located. Now what we are going to do is we are going to find the function value f computed at this particular point. Okay. So that function value is going to be f computed at yi plus q multiplied by h multiplied by f plus q multiplied by h multiplied by f. Okay. That is the y coordinate for the computing the function. The t coordinate for computing the function is going to be ti plus p times h. So this is ti plus p times h, that is the t component, and yi plus q h f is going to be the y component. Okay. So this is the slope that is computed at this yellow point. Okay. So the slope computed at this yellow point perhaps is going to look somewhat like this. Okay. So the slope computed at the point yi ti is this white arrow over here. The slope that is computed at this yellow x, we are going to just show that as this yellow arrow. Okay. And what Runge-Kutta method is, Runge-Kutta second order method is going to do is to find some kind of a weighted sum of this slope multiplied by w1 plus this slope multiplied by w2, and that weighted slope is what the RK2 method is going to use in order to project the point in the future, and the point that I am representing by the red x is going to be our y I plus 1. Okay. So that is going to be the geometric interpretation of the Runge-Kutta method. Okay. The red arrow that I have shown over here is a weighted sum of the white arrow W1 multiplied by the white arrow plus W2 multiplied by the yellow arrow. Okay. So the white arrow we are going to represent as K1 and the yellow arrow we are going to represent as K2. Okay. So I am going to say K2 is going to be equal to f of this guy, and I am going to write K1 is going to be equal to f at yi comma ti. Okay. So f is nothing but K1 is nothing but the slope computed at yi comma ti. Keep in mind that what we are doing over here is we are using yi plus q times h times f computed at yi comma ti. F computed at yi comma ti is nothing but K1. Okay. So I am going to erase this f that I had written over here and write this as K1. Okay. So now this becomes the Runge-Kutta, the two slopes required in using the Runge-Kutta second order method, and the actual S is going to be equal to nothing but weight W1 multiplied by K1 plus a weight W2 multiplied by K2. Okay. So now let us look at the unknown quantities that are there in the RK2 method, which we need to now figure out how to find these unknown quantities. The unknown quantities of course are the two weights W1 and W2, as well as this particular fractional distances P and Q. Okay. So these are the four unknown quantities. Okay. And we need to figure out a way how to find this unknown quantities. When it comes to numerical techniques or computational techniques course, one of the things that I used to joke with my students was essentially that whenever we need to find out ways to get these unknown quantities, if you do not know anything else, just use the Taylor series expansion. This perhaps most of the approximations are based on the Taylor series expansion for most of the things that we are going to look into in this computational techniques course. So again we will resort to the same Taylor series expansion. So again we are going to resort to the Taylor series expansion in order to determine what values this should W1, W2, P and Q take for the RK2, the second order RK method. Okay. So the formula that we are interested in getting is yi plus 1 equal to yi plus h times s yi comma ti. That is the formula we are interested in getting. So one obvious thing that we are going to do is expand or get a Taylor series expansion for yi plus 1 around the value at yi. So yi plus 1 is going to be equal to yi plus delta multiplied by dyi by dt plus delta squared multiplied by dy squared by dt squared, and so on and so forth. What the delta is? The delta is nothing but our h. So yi plus 1 is going to be equal to yi plus h multiplied by dy by dt computed at yi plus h square by 2 factorial d square y by dt squared computed at I plus h cube by 3 factorial d3y by dt3 at I plus so on and so forth. Okay. Now dy by dt computed at I is nothing but f of yi comma ti. Recollect that what the equation that we are trying to solve use the ODE that we are going to trying to solve is nothing but f of y comma t. Okay, so this is the original problem. That we are trying to solve. So dy by dt computed at I is nothing but the value f computed at the location I, f computed at yi comma ti. Now the next question is, what is d square y by dt square? That is something that we need to find using integration, using the differentiation by parts. So we will have d square y by dt squared. The chain rule that we will implement is going to be d by dt of dy by dt, or that is going to be d by dt of f y comma t, which is going to be nothing but dou f by dou t multiplied by dt by dt, and dt by dt is 1, plus dou f by dou y dy by dt. Okay, the chain rule is going to be d by dt of f is dou f by dou t dt by dt plus dou f by dou y dy by dt, and dy by dt is nothing but our function f. Okay, so d square y by dt squared is nothing but partial f by partial t. I will write that down as ft, plus partial f by partial y, I will write that as fy multiplied by f computed at yi comma ti. Okay, so that is going to be d2y by dt squared, and so on and so forth. For RK2 method, we do not need to expand this particular term. So this particular term, all these terms, I will just write them as OH cubed. Okay, so if we discard all these terms, the order of accuracy that we are going to get is the accuracy of h to the power 3. What we will show in a few minutes from now is that indeed these are the terms that we are going to discard, these are the terms that we are going to retain, and therefore the RK2 method has an accuracy of order of h cubed. Okay, so this is the equation, one equation that that we have obtained, and that we will I will just write that down over here. So yi plus 1 is going to be equal to yi plus f computed at yi comma ti. So f computed at I multiplied by h plus h square by 2 factorial, or h square by 2 multiplied by f of t multiplied by f of t plus f of y multiplied by f computed at yi comma ti plus order h cube. Okay, what I have done is I have just written down this particular expression over here all over again. Okay, so this is the Taylor series expansion for the true value at yi plus 1. Okay, now let us go back to the type of problem that we are trying to solve using the Runge-Kutta method. The problem that we are trying to solve with the Runge-Kutta method is yi plus 1 equal to yi plus h times s, where s is w1 k1 plus w2 k2. Okay, so we will write that down for RK2 method. Okay, for RK2 method, yi plus 1 is yi plus h times w1 k1, and k1 was nothing but f computed at yi comma ti. So I will just write that down, f computed at yi comma ti plus w2 k2. Okay, So this is what we have. Now K2, we will also write down the expression for K2. Okay, we go back over here and we find that the expression for K2 is f at yi plus qh k1 comma t plus ph. Okay, so in time we have ti plus p multiplied by the delta t, and in space in y in the dependent variable we have yi plus q multiplied by delta y, and delta y is nothing but h multiplied by k1. Okay, so K2 is going to be f computed at yi plus q h k1 comma ti plus ph. Okay, now for this again we can use our Taylor series expansion, and of course the Taylor series expansion is going to be around f of yi comma ti. Okay, so this we can be written as f of yi comma ti plus we have q h k1 multiplied by partial f by partial y plus ph multiplied by partial f by partial t Okay, so this is the 0th order term, these are the first order term in y and in t respectively, and we have the second order term. For now we are going to ignore the second order term and we will just write them down as the error term, and the error is of the order h squared. Okay, we will have h squared multiplied by d square f by dy squared, h square multiplied by df dy d square f by dy dt, and then we will have a term in d square f by dt square. All those three terms will be there, that will be the second order term. Then we will have third order term, fourth order term, so on and so forth. All those we have clubbed them as order of h square. Okay, so now what we can do, f of yi comma ti, we will just write this as f computed at I plus q multiplied by h multiplied by k1. Remember k1 was nothing but f of yi comma ti, so we will write this as f computed at I multiplied by fy, that is partial f by partial y, computed again at yi comma ti. Okay, so this is what we get for this particular term, and for this term we will have p multiplied by h multiplied by f of t computed at I. Okay. Okay, so that is what K2 is going to be. Okay, so what now I will do is I will take this K2 and substitute it over here, and then we will do the further expansion. Okay, so I am going to replace this K2 by this particular Taylor series expansion. Okay, so it is going to be W2 multiplied by f computed at I plus q h multiplied by f and multiplied by fy okay, plus ph multiplied by ft at I okay, plus O of h squared okay. So this is what we will get for the RK2 method as yi plus 1 as yi plus h multiplied by the first slope plus the W2 multiplied by the second slope. In the second slope again we have used the Taylor series expansion. Okay. What I will do is I will erase this this part that I have written over here, and I will continue with the derivation. Okay, so this can be written as, now we will have this term yi, okay. The next term is going to be in terms of f of I. So what we will do is collect all the terms involving fi only, not df by dt, not df by dy, but only the term containing f computed at yi comma ti, okay. So we have h multiplied by w1 multiplied by f computed by at yi comma ti. So we will have this h multiplied by w1 multiplied by f computed at I, okay, plus the other term that is computed by at I is h multiplied by w2 multiplied by f computed at I, h w2 multiplied by f computed at I, okay. So what I will do is I will just strike out these two terms, so that we know that we have taken care of those terms in this particular equation, okay. Then I will collect the terms in fi multiplied by fyi, that means function f computed at yi comma ti multiplied by dou f by dou y computed at yi comma ti, and I will write that with a yellow color chalk. So this is h multiplied by q multiplied by h multiplied by f multiplied by fy. So that is q h squared fi and fyi, not ft. fyi. So I will just again with a thin yellow strike, I will just cut this particular value off as well. Now I have the terms that are remaining are these two terms. I will write down these two terms with red and purple color chalks. So this is going to be h multiplied by p multiplied by h multiplied by ft. So that is p h squared multiplied by ft computed at yi comma ti. That is the red guy over there, and I will just strike off that red guy, and the final term is going to be h multiplied by order of h squared, and that we are going to write as order of h cubed. What does order of h square means? That the leading error term has h square multiplied by some other quantities. Now h squared multiplied by h multiplied by some other quantities leads us to h cubed multiplied by the same other quantities. So order of h cubed represents, that is the leading term that we are going to throw away if we do not if we only incorporate the terms in white, yellow and pink in our final expression. We will just strike this out as well. So yi plus 1 for the RK2 approximation is going to be of the form yi plus this guy plus this guy plus this and the terms that we are going to throw away. The Taylor series expansion for yi plus 1 is this plus this plus this, and this is the term that we are going to throw away, okay. So the term that we are going to throw away, keep in mind, is order of h cubed, okay. So I will write this down right now. So now what we see over here is that the terms that we are going to throw away, the leading term in that is of order of h cubed. The leading term in the terms that we are going to throw away here also is of the order of h cubed. So I will write down this information right away, and I will say that error in RK2 is order of h cube, okay. So we will keep this information for future, and right now we are not going to worry about this particular term. So I will just erase this slightly so that it is not very visible to us. It's there on the board, but we don't have to worry too much about it, okay. Now we are going to compare the individual terms in this expression and in this expression. Now these terms are the same, we don't have to worry about it, okay. Now there is a term in h multiplied by fi, and the terms in h fi are basically these terms over here. So for this expression, to represent closely the approximation that we get using the Taylor series expansion, the coefficients over here have to be the same as the coefficient over there. So for the white color guy that we have over here, the coefficient is going to be h multiplied by w1 plus h multiplied by W2, and that is going to be equal to h. Okay, so that is the first equation, W1 plus W2 equal to 1. Okay. Now let us look at the yellow colored term. The yellow term over here is q multiplied by h squared. The corresponding term in the Taylor series expansion should have f multiplied by fy at both computed at I. So we have f multiplied by fy computed at I. The coefficient for that term is h squared. So we will write qh squared equal to h squared divided by 2 factorial, and that would give us, I think I missed out the w factor over here. Okay, so the W2 factor I have missed out. I will just write that down right now. And likewise I have missed the W2 factor over here also. W2 multiplied by p h squared multiplied by f of t. So what we get, the next equation that we are going to get over here is going to be W2q will be equal to 1 by 2. Okay, and the third expression that we are going to get is W2p h squared is going to be equal to h squared by 2. Okay. So the three equations that we get for the RK2 method are these expressions, and when we ensure W1, W2, P and Q satisfy these equations, the method that we are going to get is going to have an error of the order of h cube. Okay. So that is the whole idea behind RK2. Now one thing that you will notice in RK2 is that we have 4 unknowns W1, W2, P and Q, but we only have 3 equations. What that means is that we are now free to choose any one of the parameters according to our choice, and based on that particular choice we will have various different RK2 methods. Okay. So let us now go back to our geometric interpretation and see the various different RK2 methods that we are going to get. Okay. Okay. So what I have done is all these conditions W1 plus W2 equal to 1, W2q equal to half and W2p equal to half, I have written them down over here, and let us look at the various different methods that that can come out of this particular scheme. Okay. The first method is what we had considered towards the end of the previous lecture, and that method was the midpoint method. So in midpoint method, if you recollect what we did in the previous lecture, is we said that this point is going to be midway between Ti and Ti plus 1. We took this point as Ti plus half. What that means is that P is going to be equal to half, 1 minus P is also going to be equal to half. So for midpoint method, what we chose was, we chose P equal to half. When we choose P equal to half, our W2 is going to be equal to 1, okay, and our W1 is going to be equal to 0 from this particular equation, okay, and our Q is also going to be equal to half. So Q is going to be equal to P is going to be equal to half. So the midpoint method that we talked about yesterday was that we discard the K1 completely, we only use K2, okay, and we are calculating K2 at the midpoint between Ti and Ti plus 1. That was the midpoint method that we obtained. So I will write down the expression for midpoint method. Yi plus h k1 by 2 comma Ti plus h by 2, and S is going to be equal to K2, okay. So the slope that we will use for midpoint method is nothing but the slope that is computed at the midpoint, and since P is going to be equal to Q, these points are going to lie on this particular line always, okay. That is one thing that we will see from the RK2 methods, is that if we look at these two equations, P is always going to be equal to Q. What it geometrically means when we say P equal to Q is that the yellow cross that we had shown at an arbitrary location in this particular rectangle for RK2 method does not appear at an arbitrary location, but it always appears on this particular line segment that joins yi plus 1 yi comma Ti and has a slope equal to f of yi comma Ti, okay. So this point is always going to lie on this particular curve. That is one of the things that we get out of the derivation for the RK2 method. The second possibility is what is known as Yuen's method. This Yuen's method will show later is kind of similar in some, the idea is kind of similar to our trapezoidal method for doing the integration. In Yuen's method, what we do is we choose our P equal to 1. That means the slope first K1 is of course computed at this point, the slope K2 is computed at the projected point, which is going to be f of yi plus hk1 comma Ti plus h, okay. So for the Yuen's method, our K2 is going to be equal to f of yi plus k1h comma Ti plus h, okay. That is what the value of K2 is going to be. So the P is going to be equal to Q is going to be equal to 1. If P is 1, our W2 is going to be equal to half, and if W2 is half, our W1 is going to be equal to half as well. So W2 is half and W1 is also half. So Yuen's method that we are going to get is going to be S is going to be half of f of yi comma Ti plus f of yi plus hk1 comma Ti plus h, okay. Why I said that it's kind of equivalent to the trapezoidal method is because the slope at this, the red slope that we compute over here is nothing but an average of the slope K1 that is computed at this point and slope K2 that is computed at this particular point, okay. So that is going to be our Yuen's method. There is another method called Ralston's method. And in Ralston's method, P and Q are chosen as equal to 3 by 4, and when P is going to be equal to 3 by 4, our W2, so W2 is going to be 1 by 2 multiplied by 4 by 3, which is going to be 2 by 3. So W2 will be 2 by 3 and W1 is going to be 1 by 3, okay. So in Ralston's method, what we do is we take the slope or the white slope over here, okay. The point that is projected is going to lie 3/4 of its way towards this particular vertical line. That's where this particular guy is going to lie, okay. Then we will find out the slope at this particular point, and the red slope is going to be an average, a weighted average of K1 and K2. The weight for K1 is going to be 1/3 and the weight for K2 is going to be 2/3, okay. So this is essentially what I wanted to cover with respect to RK2 method. The RK2 methods have an accuracy of order of h cube, okay, and this is nothing but the truncation error. We are not talked about the round of errors, okay. There are two types of errors that we have always been saying in this entire series of lectures. The first one is the truncation error and the second one is the round of error. In case of ODE, numerical solutions of ODE, there are actually two types of truncation errors, and this particular truncation error is known as local truncation error. Okay. The other type of error is known as the global truncation error. We will not talk about the global and local truncation errors in this lecture, we will cover them in subsequent lectures, okay. So the RK2, the accuracy is of order of h cubed, it uses 2 points yi comma ti and another point between ti and ti plus 1 in order to compute the slope, okay. So the slope is computed as the weighted average of the two slopes, okay. The first slope computed at yi comma ti and the second slope computed at an appropriate location between ti and ti plus 1, lying on the straight line with a slope equal to k1 connecting ti to a point in ti plus 1. So the second point lies along this particular line itself, okay, and the three expressions that the RK2 conditions are going to satisfy are W1 plus W2 equal to 1, W1 W2 multiplied by P equal to half and P equal to Q, okay. So that those are the things that RK2 method is going to satisfy, okay. So that finishes today's lecture. In lecture 3 in this particular module, what we are going to consider is now that we have derived the overall expression for RK2 method, I will quickly derive the expression for the Euler's method and show that the Euler's method is less accurate than the RK2 method. I will then talk about higher order RK methods and describe how to derive these higher order RK methods, and I will talk about why a fourth order RK method is actually the most popular method, and after that we will go on to Microsoft Excel and pick up the example, the plug flow reactor example that we had done during the 6th module. I will take up that particular example and solve it using the Euler's method and using the RK2 method, and we will also see the effect of changing the step size h on the accuracy of the solution that we are going to get, okay. Thanks.